Welcome everybody to the Classical Mechanics Equation Sheet Study Guide. This is going to be going through the equation sheet. This is my strategy. I think the biggest return on investment, if you're completely lost with the class, start here and you're going to be chilling. At least you're going to pass the exam. I strongly believe anybody that does this technique can pass the class. If you understand basic English and if you remember the equation sheet, you're going to be chilling. The reason is if you read a problem and it says something, find the force, find the linear momentum, any one of these words that you learned from the equation sheet, the first thing you can do, which is going to get you some part marks, I promise you, is take the equation that it's talking about. Let's say we're talking about moment of inertia. Which one of these equations talks about moment of inertia? I don't know. If I know, take that, put it on the problem, draw a little picture, write some words in English. Like I could literally just explain what my confusion is with the problem. You're going to get some part marks and you're going to get enough part marks to pass. I promise you. Never leave anything blank on the final exam. Always write something. And the first thing you can write is an equation. So today we're going to go through this very quickly. I might not get through everything with perfect detail that you guys want, but at least I'm going to give you some kind of starting ground. If you have any questions, leave them in the comments below. Try to do this on your own. Try to prepare and keep refreshing your mind on this because this paper is going to be in the final exam with you and it's going to be very useful if you remember everything. That being said, let's go through this. Here's the formula sheet. It's an example formula sheet I got from the internet. It is related to classical mechanics and we're going to go through and talk about each equation on its own. I'm just going to start from this, go all the way down, and once we finish we're going to go here and go all the way down. And I think that should be good enough. I'm going to try to zoom through, but I also want to talk about stuff in detail. So over here what we can see is x, which normally is position, linear position, f, which means final. So this is the final position, and it has a little thing over here. This means a vector. So a vector means this thing can have an x position, and it could have a y position, and it could sometimes even have a z position. But most of the time you guys are going to have some projectile moving in the x and in the y. So this little vector symbol just means you can split this equation up and then put little symbols here in the x direction, in the x direction, in the x direction, and then have a second equation where you put in the y direction, in the y direction, in the y direction. This just means position, final. So this equation here is telling you how can you find the final position of some object, a bike, a car, a ball, whatever it is, if you were given the initial position. Most of the time the initial position, depending on how you set up your coordinate system, is going to be 0. If you're given its velocity, so this is normally in meters per second, and if you're given a time over which this velocity is applied. Okay, I think that's it actually. I'm going to just write some stuff. This means position, this means velocity, and this means time. And velocity normally has units of meters per second. Time normally has units of seconds, and position has units of meters. So check out how the units work. We have here something meters per second. It's being multiplied by something with units of seconds. The seconds cancel out, and you have meters over here. So the units of this entire VT thing is meters, and the units of this thing normally is in meters. If you have meters and you add it to meters, you get meters. Make sure your units are good. Sometimes they're going to mess you up, give you something in centimeters, give you something in kilometers. The final answer is going to ask for meters. Make sure you know how to convert between things like that. Awesome. We're going to keep zooming through. Here we have another similar equation, except it's for velocity. If you have the final velocity, if you're looking for the final velocity of an object, and you're given the initial velocity, and you are given an acceleration over a specific amount of time, this equation will help you find. Or if any of these are unknown, let's say you want to find the final acceleration, you have an initial velocity, a final velocity over some period of time, you can find the acceleration. Let's say you have an initial velocity, a final velocity, and you're looking for the acceleration after some amount of time, you can solve for this. So I'm going to just write this down. Maybe I should use a small thing here. So this is velocity again, this is acceleration, and this is time. And acceleration normally has units of meters per second squared. So the units are a little strange here because now we have meters per second squared multiplied by time, right? Here is the acceleration, meters per second squared. It multiplies by time, which has units of seconds. So one of these seconds cancels with one of these. So the units left over are meters per second. But if this is meters per second and the velocity, as we said before, is in units of meters per second units add up with meters per second units, and they spit out a meters per second unit. So now anytime you see the word velocity, the word acceleration, the word time, you can just check out these equations, boom, put it on the thing. Halfway there, I promise you guys. Let's take a look at this one. This is, oh, by the way, I don't know if this is too important to remember, it might be too much information, but this is for particle under constant velocity, particle under constant acceleration. And here we have particle with initial velocity under constant acceleration. So this equation normally is used when objects are falling. Here you have x final, which is the final position, x initial, which is the initial position. You have the initial velocity over some period of time. So if I throw a ball, it starts in my hand, we can say that's position 0. Whatever I throw it with, this velocity is what goes in here. This amount of time is like, if you want to find the position after like 10 seconds, you put 10 seconds in here. Then you have here 1/2, everybody knows what this is. A normally here is g, which is 9.81 meters per second squared. You don't even need to remember this because g is over here. Boom, you see this? So whenever you see g in all of these equations, you can put that there and there. There's g in many other equations here and whatever. But I think that's the only g. And then here you have t squared. So I think all the symbols here are known. We know all the names of everything here. I'm just going to keep going. Here we have the same kind of linear kinematics equations. Like all of these are kinematics equations. I'm going to put a nice colorful box around this to group everything together because it's nice to chunk things. I think for me it's easier to remember things if they're chunked down. So take a look at this. We have a final velocity squared minus an initial velocity squared. So if you're given the initial and final velocities, you can plug that in, you can get a result. This is squared and this is squared, so meters per second, square that. The units on this side are going to be meters squared per second squared. On this side we have 2. We have acceleration, which is meters per second squared, and we have delta x. Delta x is normally the displacement or change in position. You can write this as x final minus x initial. It is just a position, so it has units of meters. So if you have meters per second squared for the acceleration multiplied by meters, these meters combine to give you meters squared per second squared, and these are the same exact units you see on this side. So anytime you're given a problem where some particle, a bike, a car, a ball, whatever, its initial and final velocities are given to you, its acceleration is given to you, and you want to find how far it travels or whatever, you could just use this equation and isolate for the unknown. Or if they tell you how far the bike has traveled and its initial and final velocities, you can find the acceleration. So just knowing the equation, what the units mean, you can isolate for things. Trust me, most of the problems can be solved this way. I know they're going to be more complicated, you're going to get stressed, but this is, if you just completely have no idea what to do, put this on the paper and write something down. Write the names. If you just write the equation down and the names of these things, you're going to get halfway there, I promise you. Plug stuff in too. We're going to do some practice problems in a future example. So I think, actually no, this equation here is also part of the kinematics equations. This is v, which normally we've seen as velocity. So this is velocity with an AVG here. This means average velocity. So I'm just going to write that down here too. Let's do average velocity. Boom. Over here we have velocity 1, velocity 2. You could use velocity initial, velocity final, whatever, and you divide it by 2. If you have 2 people in a room, and one person is 10 years old and one person is 20 years old, you add their ages together, you get 30, you divide by 2, 15 is the average age in this room. This is an average, you could do this with anything, so keep this in mind, and this completes all of the kinematic equations, which I'm going to put in a box right here, boom, like this, and I'm going to do linear kinematics. Kinematics is just equations that tell you how things move. So I've done some problems. I did like I think a battleship problem. Check this out. This uses 2 dimensions. There's a lot of complications and stuff that comes into these problems. Over here, it's obviously very simple the way I'm describing this. Like maybe they're not going to give you a simple problem where they throw a ball and they say something like find, I don't know, the position. But you'll be surprised with these equations. You can do a lot of work. So check out my battleship problem to see some examples with linear kinematics. Now we're going to move on to, I'm going to circle all of these in, let's do a different kind of blue. Let's do this light blue because these are very similar. So I'm going to circle all of these here. And here I'm going to do angular kinematics. Okay, so check this out. We've already done like a quarter of the equations. And trust me, they are very, very similar. So take a look at this. I just want to outline to you how similar these equations are. You see how here we have x subscript f, here we have theta subscript f, here we have equals x subscript I, here we have theta subscript I, here we have a v, here we have an omega, and here we have a t, and here we have a t. These 2 equations are nearly identical. The only thing they do is they change x for theta, and then they change V for omega. So this theta is an angle. Like imagine you take, I don't know, this roll of tape right here, right? If I mark this roll of tape over here and I say this is 0 degrees and then I rotate it, right? This thing, let's say I rotated like this 90 degrees. This pencil started up here and now it rotated over here. So this angle, this change in an angle is just what this theta is talking about. If I take this ball and I move it from here, this is x equals 0, all the way to here, this is x equals 5 or whatever. This is the x final and x initial. This is like the change in x here, this little change in x. So when you go to angular kinematics, you just rename things a little bit, like you use angles. This is an angle, this is an angle. So this is the final angle, this is initial angle. A perfect problem related to this is, let's say you have a DeWalt drill or like saw or something, or you have some kind of disc or like a tire, some kind of circular object spinning. They're gonna tell you, this omega is an angular velocity. So how many rotations per minute, how many radians per second. All of these things are like angular velocity. So here where we had meters per second, this is linear kinematics. When you go to angular stuff, you normally talk about revolutions per, and then there's a time over here, per second or per minute or per hour. For example, the Earth revolves once per 24 hours. So the angular velocity of Earth is 1 revolution per 24 hours. Or you can convert this to radians. How many radians does Earth spin? 1 revolution is equal to 2 pi radians. Or how many degrees does the Earth spin? 360 degrees is 1 full revolution. So you could talk about this in revs or rads, radians, or degrees. So you want to know how to convert between these. 1 revolution is equal to 2 pi radians, and that is equal to 360 degrees. So if you know this, you should be able to convert between them. This is the same way as converting between seconds and minutes and hours. If you know how many seconds are in a minute, and if you know how many minutes are in an hour, you can figure out how many seconds are in 24 hours. Try to see if you can convert this stuff. A lot of these problems, especially the first example problem you see with this, where you have some kind of wheel spinning, I don't know, 20 revolutions per minute or something like that for a specific amount of time. Find how many radians or revolutions it has traveled after like 10 seconds or 20 seconds. A lot of these problems are testing your ability to convert between units, because this equation is very simple. You just plug numbers in, boom, you get the final answer, which is the theta normally. Or if they tell you, okay, we start at theta equals 0 and we rotate the wheel 375 degrees, so like a little bit more than a full turn. This happens after 20 seconds. What is the angular velocity of this thing? So I'm just kind of yapping over here, but let me write over here. This is an angle. I'm just going to call it like this, angle. So this is normally revolutions, or let's use radians, or let's use degrees. So now it gets a little more complicated because there's different like units. Over here we just had meters, and then over here this is angular velocity. It could be rads per second, or it could be revs per minute, or it could be degrees per second or something like this. Any kind of like angular velocity. Same thing here. Your car doesn't give you velocity in meters per second, it gives you velocity in kilometers per hour. But most of the time in physics, we like using SI units. So instead of kilometers, we like using meters. And instead of hours, we like using seconds. So you want to be able to convert between these, and you should be chilling. Anyway, I'm going to zoom through these equations. If you have a final angular velocity, let's say the DeWalt saw is spinning like 20 revolutions per second or something. I don't know how fast the DeWalt drills spin, and it started at rest. At rest always means 0. Find its acceleration. If the time that it takes for it to go from rest to whatever this number is was 20 seconds, you find the angular acceleration. So this little, you see how the A is a little different? This is a Greek A, it's an alpha. This is a little different than just this regular A over here. So this is kind of how you can distinguish between them. This is Axel. I'm just going to write it like that. Same thing here, okay? Final angle. how many angles or revolutions has this thing spun finally. So this final thing depends on all of these. This is an initial theta. This is the initial angular velocity. This is the amount of time it has spun for. 1/2. This is the angular acceleration, and then t squared. So plug all those values in and see how this works. Same thing, same equation here. So this is why I circled both these together. This equation here matches with this one perfectly. This equation here matches with this one perfectly, and these two match with this one perfectly. And then same thing here. You know what? Now that you guys know all these symbols, I'm just gonna skip through this because I think you guys are chilling with this. So this is amazing. We went through a quarter, and this is like kind of midterm stuff. Like this is before the midterm, and this is a little bit after the midterm. But this is important because you're for sure gonna see a problem related to at least this over here, if not this, because this here is midterm stuff, but this is post-midterm stuff here. These two equations. Now look, these two equations, I don't know what they are. I could take a guess. I'm going to take a guess, and I'll tell you why I'm making this guess, but I'm going to put these two in their own color, which is pink. So what I think this H means is height, and I think this R means radius, but I could be wrong. But I know that these things have units of meters. And if you know the units, this is going to help you out quite a lot. So here's why I'm saying this. Here you have a v, right? This is velocity. This is the initial velocity squared. Here you have a sine squared theta. Sine of theta is always unitless. Trigonometric identities don't have units. So this entire thing here has no units, right? Over here 2 has no units. G, if you look over here, has units of meters per second squared. So if I have something in the top, which is meters per second, this is the units for velocity squared, and I divide this by something meters per second squared, what I have is meters squared per second squared, and then the denominator I can flip, do some like cross multiplication, and I get this. So you can see these seconds squared cancel with these seconds squared, and one of these meters cancels with one of these. So check the unit analysis here. What you get is meters. So I know that this H has units of meters. This is already going to help you a lot if you don't know what this equation means. What does this mean though? I don't know. Like what I'm remembering is something related to, I think, angular momentum or rotation of rigid bodies, because I remember some kind of problem like this where this wedge is angled with something like this, and you have an object over here rolling down with an initial velocity or something like this under gravity, so gravity is pulling it down. And then this H is, I don't know, like height. I'm not too sure, but I'm going through this like first kind of glance. So if I find some correction, I'm going to put it up right over here. But if you guys have the same confusion as me, please check it out. Same equation down here. It looks super similar. They remove the 2 and they remove the square onto this sign, and they add an extra 2 inside the sign here. But the V here stays the same, v squared initial. I'm assuming this is initial velocity, and this g stays the same. So everything stays the same, like all things with units stay the same. So this thing also has units of meters. But I don't know. Radius, I might have to double check, but if you find any problem where there's like some theta, some initial velocity, this, and you know what this equation is talking about, you could just take this equation, put it in the problem, plug some numbers in, and just write something like, oh, I think the angle has something to do with this. You should be chilling. But I'm not really too certain about these, so I'm going to, again, give you guys an answer of what this looks like somewhere over here. Okay, moving on. This is a very important equation, and this equation is honestly gonna, you could expand this equation like endlessly, I'll be real with you. This is Newton's second law. So I'm gonna just write this down here. Newton's second law. So F over here, this is a force. And this has units of newtons. Alright, that's important. This is mass over here. Mass has units of kilograms. Those are the SI units. And this is acceleration. I'm just going to do accel, which has units of meters per second squared. If you forget the units for acceleration, just check out the acceleration due to Earth's gravity. This is normally something that you replace A with, and it has the proper units for acceleration. So I hope that's good. And just knowing like the name it's not going to help you too much, but one thing that's helpful with the units is with this equation, you know that 1 Newton is equal to 1 kilogram times meter per second squared. So this equation can help you convert SI units into newtons, which are non-SI units. There is a lot of problems using Newton's law, so many problems. So just knowing the equation, it's maybe going to help you out, but there's a lot of tricks that can kind of like come out of this equation that you probably won't learn about it just by knowing the name of the equation. But right now I just want to study the equation sheet. I just want to know the name and all the symbols and stuff inside the equation. And next we'll look at some problems. Check out my classical mechanics playlist. You should see some videos over here where I use Newton's second law. We're going to keep zooming because I think I'm spending too much time here and there's a lot of stuff to talk about over here. So we're going to go to this equation over here, which I will put in the same, no, let's put it in a green. So this F is force of friction, and this is super important. If you see anything related to friction, this equation automatically will come up. And this mu over here, this Greek letter mu, is the coefficient of friction. Sometimes it's going to have a subscript S for static friction, sometimes it's going to have a subscript K for kinetic friction. It doesn't matter, it's just a number, it's unitless. And this N over here, I normally write it with a capital N. It is the normal force. So the normal force is the force that an object feels from the surface that it's resting on. So if I'm sitting in my chair, I weigh like 180, I am being pulled down by gravity. So I do my mass, 180 pounds, let's do like 80 kilograms times G. That is the force that I'm being pulled down on Earth, right? My chair has to push up by the same amount because I'm not like falling and I'm not rising, right? So by Newton's second law, I have no acceleration, I'm just resting my chair. So this normal force that the chair is pushing up on me is the same as my mg pushing down on it. And in friction, if something is very heavy, it's gonna feel more friction when you try to drag it. Like imagine dragging like a tiny little pebble by a string on grass. It's gonna feel some friction due to grass, right? But if you drag a huge boulder on the grass, it's gonna feel much more friction. So that's why this friction force depends on the coefficient of friction. If the coefficient of friction is much greater, coefficient of friction is like 20, you're gonna feel a bigger force of friction. And if the normal force, so how much your object weighs and is being pulled down by, and how much the surface underneath it is pushing up on it, if that is bigger, then you're going to also increase your force of friction. Hopefully that's okay. We're going to move on to this next thing, which I'm going to put in light blue over here. And this P over here is linear momentum. Linear momentum. There's again a lot of things we can talk about here. Linear momentum has units of kilogram meter per second. And the way I know this is because the other side of this equation, oh man, we're going to get a little messy here. This m is mass, so it has units of kilograms. Let me just write mass. And this v is velocity, velo, which has units of meters per second. So if on one side of the equation I have mass times velocity, mass in kilograms, velocity in meters per second, then linear momentum, which is this p, it is a vector, right? Because linear momentum has x and y coordinates. Like if I shoot a billiard ball and it's moving, depending on how you set up your coordinate system, the billiard ball is going to be moving both in the x and the y direction. Like if you have your billiard table, right, and it's like this, and one flat side is called the x coordinate and one long side is called the y coordinate, and the billiard ball is moving diagonally. It has momentum, a mass times a velocity, in the y direction and in the x direction. If you're scared about vectors, I have a vector video over here. You're going to learn a ton of stuff about vectors. Check this out if you're interested. But a lot of these things, anywhere where you see a vector, over here, over here, over here, over here, all of these little vectors right here, and these vectors right here. Check out my vector video. And also I talk about this dot product and cross product in depth in that vector video. So check that out. But this is linear momentum. And there's, again, lots of problems related to Newton's second law and linear momentum. But as long as you know the equation, I think you're going to be chilling. But that shouldn't stop you from studying more, please. But if you don't have more time to study than just watching this equation sheet video, I think you'll be chilling. Now we get to something that's kind of confusing that I really want to stress. There is two places where you see this capital I. This one specifically is impulse. So anytime you see impulse, the word impulse, this is the only equation that has impulse in it. This is spelled impulse. What does impulse equal? Check out the equation. This big sum just means add up. What do you add up? Add up all of the F. What is F? F is a force, an average force. Add up all of these average forces and multiply by this delta T. So it is a force times a time. If I punch somebody, I'm applying a force over a super small period of time. So it's a small impulse. If I increase the amount of time that this punch is being applied to, the impulse increases, right? Because they're directly proportional. You see I equals, if this T goes up, this I goes up. If this T goes down, the impulse goes down. If the force applied, if the punch is with bigger force, this impulse will go up. If the force goes down, the impulse will go down. So the only way I can describe an impulse is a force applied over a period of time. The only problem I've seen related to this is a car crashing and the front of the car crumples, and they're telling you, why does the car crumple? It is to reduce the impulse, because if the car didn't crumple and it just hit the wall and the car was made out of like adamantium or something, the car would just hit the wall and all of that impulse would be sent into your body. It would just fly away. This is very bad. When you crash in a car, you want the front of the car to be crushed and absorb all of the shock so that you like kind of just jolt a little bit. If your car doesn't crumple, you're going to screw yourself up. So I don't know, check out this problem. I don't know which chapter impulse is in, but the only important thing here is impulse. What are the units here? I don't know. I think just by looking at the equation, we have a force, which is units of newtons, times time, which is seconds. So newtons times seconds. I don't know. I think that's all I got here. And they got this delta P over here. This delta P, I think, means change in momentum. And momentum has units of kilogram meters per second. Interesting. So if they tell you that impulse is equal to force times time, and force has units of newtons and time has units of seconds, but then they also tell you this I is equal to the change in momentum, then it looks like these units and these units should match. Is that true? Let me show you guys a 200 IQ trick. You see how there's seconds over here and there's seconds over here? But there's newtons over here and there's kilograms and meters over here. So you want to find a recipe to help you check if newtons can help you convert into this kilogram meters. How can you do this? We're going to use the equation that has newtons in it, the favorite equation, the best equation ever. F equals ma. I literally got this equation on my shirt. Peep this. So F equals newtons. Ma is kilograms meters per second squared. So here we can see the recipe for 1 Newton is equal to kilogram meters per second squared. I'm going to now take this equation of impulse, newtons times seconds, and I'm going to plug in this recipe for newtons. So instead of this n, I'm going to do kilograms times meters per second squared, and then I'm going to replace whatever's left. This seconds, this stays the same. Now check out what happens here. There's 1 second over here at the top, and then seconds squared at the bottom, so this second cancels with one of these. And then we're left with kilogram meters per second. Kilogram meters per second. And check this out. That is exactly equal to this, kilogram meters per second, kilogram meters per second. So I showed you two very important things. First of all, impulse can be written in 2 different units, or in 2 different ways. If you have something with impulse and they give you momentum, you could use this. If they have something with impulse and they give you force and time, you could use this. Also, converting between units is super important. So if you know this trick where you take an equation and treat it kind of like a recipe, like what does newtons equal, and then you use this and then you plug it into your equation and then like simplify a little bit. You can simplify and then kind of get some interesting stuff out of it. This is why my favorite way of studying is to just look at the equation and write down the names and the units, because if you know the names and the units, most of the time your math is going to be chilling, and most of the time you kind of know where to start with a problem. So that is a lot of yapping. I'm sorry, I'm trying to give you guys as much interesting stuff as I think might be useful, but I don't know, maybe this is not too useful for you guys, I'm not sure. I think it's useful. This is how I studied and I finessed final exams. I actually, by the end of my studies, I loved doing final exams because I was cooking heavy. So we're going to go on here. This W, I'm going to circle both of these in red because they both mean work. Work. Any problem that has the word work in it, find how much work this guy does. Find how much work is done by this. This is the only place where work is found. Let me see. No other places are you going to find W. But this might actually be a little trick, because I remember when you learn about work, you learn about the work energy conservation theorem, which is nowhere to be seen in this equation sheet. So that's something that springs to my mind. If we don't see this, then how are we gonna know what equation to use? Don't stress about that. We're gonna take a look at it in a little bit, but for now we're just gonna study with the equation sheet. Work normally has units of Newton times meters, I think. The reason I'm saying this is because check out what this equation is telling you. Work is equal to this F, which we saw from before. F over here is equal to force, right? And force has units of newtons. So that's why I write this newtons here. And then this little dot is supposed to be a multiplication symbol. This, actually, since these are vectors, this is actually the dot product, which is shown over here. So no need to worry about this, but maybe it's important. But you see these two vectors. These two vectors can be just plugged into here. This A and B are very general. Here you have A, here you have B, the magnitude of them, and then this little cosine theta is the angle between these two vectors. So if this is vector A, this is vector B, or in this case, this is the force vector, and this is this little delta R vector. This angle is the angle between them. So this is important whenever you see the dot product. And in this case, the dot product is here between two vectors. The only way you can multiply two vectors together is with a dot product or a cross product. There's no other way. And it's not the same as regular, like multiplication 4 times 3 or whatever. So anyway, this delta R is the same thing as this little delta X. X and R and B, most of the time they use these symbols and letters to represent position or distance or something like this. So this little delta R is just like how much distance have you traveled. If you start here at X initial and then you go here at X final, this thing over here could be delta X, or sometimes they call it delta R. And if you start here and you're going this way, this has a magnitude, a length, and it also has a direction. If I create a coordinate system like this and there's a theta over here, this is why they call this a little vector. That's also why they use a bunch of vectors over here in these things. Don't stress about vectors though. Again, check out my vector video if you're interested. But this is very simply telling you, if you want to find the work done over some distance with some force applied to it, all you have to do is take the dot product of the force vector and the position vector, and the dot product has this little cosine theta in it. So if the force vector and the position vector are, or maybe displacement vector is a better name, not position vector, if they're pointing in the same direction, then theta is equal to 0 degrees and cosine of theta is equal to 1. But if they're at 90 degrees, then cosine of 90 is equal to 0. So if you plug in if they give you some angle and you check this angle and you plug it in here and the cosine equals 0, then the amount work done is 0. I don't know if that makes too much sense. I think I've done some problems related to the work. If you're interested, let me know and I can do a problem. Here we have angular work. So this was linear work, a force, a linear force. Like if I have my phone here and I push my phone, right, I'm pushing it this way. This is the force vector pushing it this way. And the displacement vector, it started here and now it's going this way. The force vector and displacement vector are pointing in the same direction. So work is done, linear work. If I push down over here, first of all, the object is not being displaced. So the delta R vector is 0. But also I'm applying force at 90 degrees compared to this displacement vector. But the displacement vector is 0, so maybe that's a stupid example. Anyway, here we have work in the angular way of thinking about it. So this T is torque. We haven't talked about torque, but you can think about it as like an analogy to force, except force is linear and torque is kind of like rotational, like the rotational analog to force. And torque has units of Newton meters. So actually, I'm just going to write this here. I'm not going to write force, but maybe here I'll write displacement, and then this has units of meters. So if you have force, newtons, and displacement in meters, you have Newton meters, and that is the unit of work. Then here we have torque. Torque, tau, this has units of Newton meters. We're going to see later because we're going to see an equation related to torque. And then delta theta is like the angular displacement vector. So angular displacement vector, this has units of radians or revolutions or degrees, but normally these are unitless quantities. Like you can write the word degree, or you can write radian, or you can write revolution, but in math equations normally they're treated as like unitless. And the reason I'm saying this is because if you look at work, it has units of Newton meters. Here torque has units of Newton meters. So we have Newton meters equals Newton meters. So this thing has to be unitless for the equality to work out. Hopefully that makes sense. Hopefully you guys aren't spooked about this, but just know anytime you see work, anytime you see torque or force or something like this, you can use these two equations here. You might be cool. Okay, dot product. Two vectors, dot product. A vector has a length and a direction. If you draw them, make sure you draw a lot of pictures in your exam. You can find the length or the magnitude or the strength or the whatever of the vector, how long it is. That number goes here. This is now just a number. This here is just a number. It has no direction associated to it. This is a vector. It has a direction and a magnitude associated to it. The dot product takes two vectors, eats them, and then it spits out just a number. So in here, all we have is just a number, no vector. The reason is this is a magnitude, a strength, or a length of a vector. You multiply that with this, which is also a magnitude or a strength or a length. And here cosine of theta is just a number. It could be 0.1, it could be 1, it could be 0.5, whatever. So if you have a number times a number times a number, and you get just a number over here. This is what the dot product does. And you'll see the dot product in a few locations like here. This one is a little bit different. I haven't seen the dot product anywhere else. Yeah, nowhere else. Here we see an equation related to the cross product. No stress about that. But like I said, if you were interested in learning about vectors in a little bit more in depth, I have a whole like 40-minute video related to vectors. Check that out. So let me just write here, dot product and cross product of two vectors. Amazing. And the cross product is a little bit more interesting. The cross product eats two vectors and it spits out a third vector. A vector has a direction. So how do you find the direction of this vector? You use the right hand rule. This is my right hand. The way I do this is I point my thumb in the direction of the first vector, vector A. Whatever vector comes first in the cross product, my thumb points in the direction. So let's say vector A is pointing this way. My pointer finger points in the direction of B. So now I point my thumb in the direction of A. It's stuck there. So B is either pointing this way or this way or this way or whatever, or it's pointing in the same direction as A. So you could see the angle kind of closes between them. But let's say they're perpendicular or orthogonal to each other. So let's say vector B is pointing towards the screen, right? This middle finger, pause on this, is pointing like up this direction. So this is the direction of the result of the cross product. So I have two vectors, vector A and vector B. I cross product them and I get vector C, which is pointing perpendicular to both. You can see this vector here is perpendicular to this vector A, and it's also perpendicular to this vector B. So this is what the cross product does. It is a machine that eats two vectors and it spits out a third vector perpendicular to both of the other vectors. You don't gotta stress about that, but check this out. If you have the length or the magnitude of vector A, and you have the length and magnitude of vector B, and you have the angle between those two vectors, you can plug this all in and you can get the magnitude of the third vector. So this equation over here gives you the magnitude of this third vector, and because the cross product eats two vectors and it spits out a third vector, and a vector has a magnitude and a direction, this equation here will give you the magnitude, and the right hand rule will give you the direction. So now we are done the entire side over here. I hope that was okay. I hope this is kind of useful to you guys. Let me know if you have any questions about any of this. Now we're going to move on to this, which is also quite heavy. And this is a very important thing. This I over here, this is the second time we're seeing I. You see this I over here? This I is very different. This I means moment of inertia. We saw I in two places. Here's the second place, and here is the first place. All right, so this is the impulse. I don't know why they use the same letter. It's just standard, but do not confuse this I impulse for this I moment of inertia. But normally in problems, they're going to say in words, moment of inertia blank, impulse blah. So if you see the word moment of inertia, automatically you must jump to this equation. If you are completely confused about moment of inertia, just knowing this and saying moment of inertia is defined as such, and you write this equation, and then you write some other random stuff related to the problem, you could just take the problem, mix the words around, you're going to get like 25% of that question correct. Trust me. Just the equation, this is what the grader wants to see. Obviously, you have to put some more effort into the problem, some more logic, get the final answer, but just start with this, you're going to be chilling. Don't leave anything blank, like I said. So moment of inertia, what does this mean? I don't think you're ever going to use this equation over here. I haven't seen any problem done with it. And actually, most of the time, the part where you have to calculate moment of inertia of different objects, which uses this equation, it's avoided. And what they actually give you is a little table of different moments of inertia over here, which we're going to look at the end, so don't stress about this. But moment of inertia is kind of like the mass of a body as it's rotating. And different bodies have different moments of inertia. You can see here, you have a hoop that is hollow, you have a hoop that is a bit more thick, you have a solid cylinder, you have a slab that looks like a chocolate bar, you have a rod rotating through the center, you have a rod rotating through one edge, you have a sphere rotating through the solid sphere rotating through the middle, and thin spherical shell. So any one of these objects, if they show you a picture in the problem and they're asking you about moment of inertia or blah, 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 you could just pull the value out of here and boom, here's what they give you. The M, which is the mass of the thing, and R, which is this little radius here. So you could pull moment of inertia. But in this case, let's just look at it. How do you calculate moment of inertia? Let's look at the symbols. Moment of inertia here, I think, has units of kilograms. And then here, I think meters squared. The reason I'm saying this is because I'm looking at the other side of the equality. Here we have mass. Let me just write mass. You guys already know we use kilograms as the standard SI unit for this. And here you have R. This normally is radius because now we've moved on to rotation of rigid objects. This is where they introduce moment of inertia. So if you have an axis of rotation, let's say the Earth rotates through its axis. So the Earth is spinning around on this axis. You want to find out how much mass the Earth has at a given radius. The Earth is a solid sphere. It has different masses everywhere. If you say the axis of rotation is through the center of the Earth, then we move just a little radius out, like maybe 1 meter or 10 meters or 1 kilometer. This is the core of the Earth. The mass there is made out of a specific molten metal. I don't know what's in the center there, but the mass there is different. So you add up all of this mass. This is what this little summation sign is saying. It's just like add up all of the mass around this little specific radius. Then you go out a little bit further. I don't know if you guys have seen a cross section of the Earth with the different like layers and shit like this. Anyway, you just add up all the mass, and then you get the moment of the inertia of a solid spherical object, which is this. You take the total mass of the thing, you take the total radius of the thing, 2 divided by 5, multiply all these things together, and you get the moment of inertia, and you could do some cool math with this. It's just like a mass. Like, you have the mass of the Earth. This is normally used for like F equals ma, some linear related stuff. But if you want to talk about rotational stuff, moment of inertia is what you're going to use. So this is what this little r means here. It's a radius, and radius normally has units of meters. So this is why I said moment of inertia has units of kilograms, meters squared, because the equation here uses mass, which has units of kilograms, and radius, which has units of meters, but they square this radius. So boom. So hopefully this is useful. I don't really think you're going to use this equation, but it's nice to know it because at least moment of inertia, now you know that the units are this. Awesome. Moment of inertia makes an appearance here and here. Anything related to rotation, moment of inertia is going to make an appearance in. It also makes an appearance here. So the more important I is the moment of inertia I. This is the one that's going to be used in most of these equations over here. This I, the impulse I, The only place it appears is this equation. So the second you see impulse, you use this equation. And the second you see moment of inertia, you have several equations to play with. You have this one that has an I in it. It's right here. You have this one, it has an I in it. You have this one, it has an I in it. And this is the definition itself of moment of inertia. Hopefully that's cool. Let's move on to these two things, which I'll circle together because they both talk about the same thing. This capital L is a vector, and this means angular momentum. Amazing, and it is a vector. Similar to linear momentum, which was over here. Linear momentum, kilogram times meters per second. It is a mass times a velocity, and this is capital P. Now we move to angular momentum, L, which is a mass times a v, but also times a radius, because we're rotating about this kind of pivot or this kind of axis of rotation. So here an interesting thing happens. L is a vector. The way it's created is you take a mass, which is just a scalar, like this is just a number, it's not a vector. The radius is a vector, because you could have a radius pointing this way, a radius pointing that way. You can have radiuses of different sizes. So if you have a direction and a magnitude, this is a radius, or this is a vector. And if you have velocity, this is also a vector. So here you have the cross product of two vectors. So if you see something like this, the cross product, you could literally just pull up this equation over here. You see how like learning about the equations already helps you a lot? Because if you see anything related to angular momentum, you can put this equation in. And now you see something related to the cross product, and you can pull this equation in. And if you don't know what's happening, you don't know how to work with the math, just put the equations down. Trust me, you're going to get halfway there, if not more than that, and you're going to pass the exam. I promise you. I mean, don't get mad if you don't, please, but I'm trying to help you guys as much as I can. Anyway, this is angular momentum. What are the units of angular momentum? Let's check. We have R times V. If we go back here to the cross product, what happens in the cross product? We have something times something. So whatever the units of this, we multiply the units of this, and we multiply by this, but this thing is unitless. So the cross product just has the units of both of the cross product vectors multiplied by each other. That's amazing because we have R and V, and we already know the units for this. We have R, which is radius, which has units of meters. We have velocity, velo, which has units of meters per second. And we have mass, which has units of kilograms, which is all the way in the front. So if we have mass, which is kilograms, we multiply this by R, which is radius, which has units of meters, and we multiply this by V, which has meters per second. Then we get kilogram meters squared per second. So now these are the units for angular momentum. Let me actually just draw a little arrow over here. I hope I'm not getting anything wrong here, but I think it works out. And we have another equation over here that also gives us angular momentum. So if you need to use two equations, you have two equations, two unknowns, and you need to solve for something, you can do it this way. You can find angular momentum this way and then maybe use this. Let's check with this equation if we get the same units as this. So what does this equation say? We have an L over here. This is again angular momentum. It is a vector. By the way, remember how I told you a vector has a magnitude and direction? This will help you find the magnitude, right? But the direction, right, because this is a vector, the direction can be found with the cross product. So check this out. We have R. R points this way, for example. V points this way, for example. That means the angular momentum points this way. Whatever way R is pointing in your problem, whatever way V is pointing in your problem, remember the right-hand rule. And if they ask you for the direction of the angular momentum, you could literally just draw a hand, and you could say, or if you're not good at drawing, I mean, try to draw a hand. No matter how goofy it looks, you're going to get part marks, I promise you. But if you can't draw, you could just say in words, this is a cross product of two vectors. So by the right-hand rule, we can determine that the direction of angular momentum is this, and then just do something like this, and then draw this. Draw little vectors and label the vectors. A picture will go a long way, I promise you. Now let's look at this other equation. This is angular momentum. Here is I, this is moment of inertia. So we already have units for this. We have these units over here. And this is omega. Omega is angular velocity, which has units of radians per second, or revolutions per second, revolutions per minute, or degrees per second, degrees per minute. We're going to keep it in SI units. So it's going to be either revolutions or radians or degrees per second. Second is the SI unit. If you're unsure what SI unit means, just Wikipedia search that, or don't stress about it. It's just standard units that are used. So let's take a look at this. I'm going to boom over here. So I is a moment of inertia, which has units of kilograms, meters squared, right? And then this has units of, like, let's say radians per second. So like I said, radians normally is not something that appears in the units. It's like kind of unitless, like angles, degrees. I don't really know how to explain that too well, but it's something to do with like arc length and radius. Like a degree is defined by like the arc length divided by the radius or something like that. And since arc length and radius are both in meters, the meters cancel out and you get the degree, which is kind of a unitless quantity. So hopefully that is not too confusing, but check this out. We get over here kilograms times meters squared divided by seconds. Kilograms meters squared divided by seconds. So now we have the units over here for angular momentum and two different equations for angular momentum. So angular momentum is defined like this. Anytime you hear the word angular momentum, write both of these equations down. And if you're completely lost, just write these equations down and write angular momentum is this, draw a little arrow, and then draw a little arrow with the name and unit for each of these. And then just put some numbers related to your problem. This is going to be very good if you're completely lost. Now let's move on to this bad boy, which you guys have seen before. This little tau is torque. And torque has units of newtons per meter. And the way I remember this is exactly this equation. So this is R, it is a radius, because torque is related to, the perfect example I imagine is like you have a wrench. Like let's say this is your car's lug nut and this is the wrench. You apply a torque, you apply a force over some distance. So a torque is exactly R cross F. This is how it's defined over here. So R has units of meters, F has units of newtons. We've already written this before, so I remember torque always has units of Newton meters. And I also wrote this down somewhere over here. Torque has units of Newton meters. And torque makes an appearance over here. So if you have a torque applied over some units, over some angles, like let's say you're trying to unscrew a lug nut on your car, you apply a torque right over here and you twist, let's say we twist like 90 degrees. Boom, now you have the work done on a lug nut by you turning it. Amazing. And here's another equation. Actually, maybe it's good to put both of these together because they both talk about the same thing. So torque can be found one way, R cross F, and it can be found another way, I alpha. You guys remember what I is, right? It's moment of inertia. This one over here. So this moment of inertia makes an appearance here, and it makes an appearance here. And it also makes an appearance way down here, which we're going to see in a bit. So if you have the moment of inertia, you can find the angular momentum, you can find the torque, and you can find here this Kr is kinetic energy of rotation, I think. So let's take a look at what's in here. You guys already know what alpha is. Alpha is angular acceleration, which has units of radians or revs or degrees per second squared. So rad or rev or deg per second squared. So this alpha is the alpha that makes its way into here. And this is why I said torque is kind of analogous to Newton's second law, because look at this equation and then look at this equation over here. F equals ma is the same as torque equals I alpha. The I is the same as m, and the alpha is the same as acceleration. So the torque is the same as force. If you remember this, you could, and you're completely lost on a problem, you could literally just say, because torque is analogous to Newton's second law, or this equation for torque is analogous to Newton's second law, then by the principles, just say random shit like this. If you're completely lost, it's better than leaving the exam blank. You know what I mean? So moment of inertia times some specific angular acceleration of your rotating object is equal to the net torque applied onto this object. So it's kind of like the net force applied to some object with mass m provides an acceleration. The net torque applied to some object with moment of inertia I provides some acceleration. If the net torque is equal to 0, then the acceleration, the angular acceleration, is equal to 0. So again, there's lots of hidden stuff related to this, but for now I'm just sharing like the most important thing. If you're completely lost, just study the equation sheet. That's the best return on investment, and then you can use these equations to practice problems, which we're going to do in the next video. Let's move on. All of these equations here, I'm going to circle together in a special color. Let's go with pink. So these equations here and this one over here. The reason I'm circling them together, let's see. All of this stuff is related to energy. So wherever you see K, this is kinetic. And then wherever you see U, this is potential. There's some stuff that they didn't put in here that's pretty important. The energy conservation equations. So I'm going to actually write this here. Energy conservation equations. I think maybe I'll put some of them up over here, but I'm noticing they're not in the equation sheet, and you can't really do anything other than just find kinetic energy with kinetic energy unless you are given the energy conservation equation. So this energy conservation equation is super important. It relates kinetic energy, potential energy, work, and a whole bunch of other shit. You need to write this equation down. This is the most important one that is missing from the equation sheet. I'm going to put it up here. Please remember this. Please do a few problems with this. For sure it's going to make an appearance. Maybe. But I think it's very important, and I'm noticing it's like one of the most important things, and it's not given to you. They just give you how to find the kinetic energy and the potential energy and stuff like that. So I'm just going to speak very quickly. I think you guys already know all the symbols here. This is kinetic energy. It always equals 1/2 mass velocity squared. So any object with a mass and a velocity, this object has kinetic energy. Any problem where they tell you this object is moving with a mass and a velocity, you can find its kinetic energy, and this kinetic energy will be helpful because there's some energy conservation stuff that's going to help you find, I don't know, it's how much a spring compresses or how high a ball rolls up an incline or something like this. So kinetic energy, 1/2 mv squared. This is UG. It is the potential energy due to gravity. If my phone starts here, it has a potential energy due to gravity, because if I move my hand out of the way, this phone is a distance off of my floor. It's also a distance off of my building. So if I drop this phone, it's going to fall onto my lap. If my lap wasn't there, it's going to fall onto the floor. If the floor wasn't there, it's going to fall all the way down to the ground, the earth, right? So this is potential energy. The object, when it moves all the way up here, you're giving it potential energy. Then when you let it go, this potential energy reduces, and it's converting it to kinetic energy, because here it is at rest, no kinetic energy, but it has stored gravitational potential energy. When it is dropped, it's going to convert this gravitational potential energy into kinetic energy, because it starts speeding up, it starts gaining a velocity, and we know 1/2 mv squared equals kinetic energy. So take a look at this. If you have m, the mass of an object, times g, the gravitational acceleration on the planet you're on. So most of the time this is 9.8 meters per second squared, because this is on Earth. If they give you another planet like the moon, Jupiter, Mars, the sun, it's going to have a different g, and it's going to have a different gravitational potential energy associated to that. This y is the height above which your object is raised. So this really depends on the way you set up your coordinate system. If I say 0, like the ground level is at my desk, then lifting my phone up over here is like, I don't know, 12 inches, 20 inches, 1/2 meter above my desk. But if I say 0 is from the ground floor where the grass is outside my building, then this is going to be like 2 stories, or like, I don't know, 15 meters or something like this above the ground. So gravitational potential energy depends on the mass. If mass increases, if I have a very big truck compared to a little grain of sand, then gravitational potential energy increases. If G increases, if I was standing on the moon, gravitational potential energy at the same height with the same mass object is going to be much less than if I was standing on the sun, where there's much bigger gravitational acceleration pulling you down. And Y, if I'm closer to the ground, like if I drop my phone over here, it's going to just gain a little bit of kinetic energy. But if I drop it from like a plane, it's going to gain a lot of kinetic energy. So this G normally converts into K. Or if you drop an object and it falls onto a spring or something, this gets us to this guy, which is the potential energy. Remember, U is potential energy. And this little S is spring. So maybe I'll write this spring, and then here gravity, and then here kinetic. I think that's all you guys need to know for this. This K is the spring constant. It's just a constant, like a number that defines how strong your spring is. If this number is very big, like 20, I think the units for this is normally newtons per meter. So if this number, you can go to Home Depot and buy a spring, it's normally going to say how strong the spring is in newtons per meter, I think. I don't know. I haven't purchased any springs, but in physics problems, normally they use this. And actually, I was just thinking, I think it's important to write this. So this newtons per meter is the K, and then here we have x squared, which is meters squared. So if you multiply this, you get Newton times meters, right? Because one of these m's cancels with one of these, and you get Newton meters. We already saw Newton meters is the unit for torque, but it's also the unit for work. And it turns out it's also the unit for energy, which is very interesting. And I think actually Newton meters is the same as joules, because I remember kinetic energy always is given to you in joules. These are like the SI units of kinetic energy. I'm not sure about this, like I'm a little uncertain, but if you just multiply these things here, you get kilogram meters per second and then squared. If you use the Newton recipe from before, I think you're going to get down to this. And then I think they take this and they convert it to joules. Please double check this. Check out kinetic energy units on Wikipedia and then see like kinetic energy, joules versus Newton meters conversion or something like this if you're interested. I don't think it matters too much. But anyway, if you have the spring constant K and you have this X is the compression or extension. So if the spring starts here and I compress this spring, an amount X, so let's say it starts here and then I compress it down to here, this is like, I don't know, 0.1 meters. Always use SI units meters. Or if I take a spring and I stretch it all the way to here, this is like, again, 0.5 stretch this way. So you take these numbers, multiply them together, and you get the potential energy stored in the spring. If you squish a spring, it's going to have potential energy stored in it, and if you let it go, like if you have a bead over here, like you squish it, put a bead, like a little marble or a little rock, and you let the spring go, the potential energy from the spring is going to convert into kinetic energy into that little bead. So you can see a ton of problems related to this. I think I solved some on video, but I'm not too sure. Check the book, do some problems. In the next video, I'm going to try to do some problems from a practice final that I found, and we'll try to see if there's anything related to this. And let's very quickly talk about this too. This is very similar to kinetic energy. So if you have like a boulder, like a meteorite in space going in a straight line, you take its mass and its linear velocity, right over here, multiply by 1/2, square the velocity, multiply everything together, you get its kinetic energy. Very similar to rotating objects. If you have the Earth is rotating on its axis. But it's also rotating around the sun, so this is a little interesting. Anyway, you take its moment of inertia, which you have over here, or if you have a specific object, you can take from over here, right? There's moments of inertia of multiple objects over here. You take the moment of inertia and you multiply it by its angular velocity squared and you multiply by 1/2. You can see it's very similar. V, omega, linear velocity, angular velocity, mass, moment of inertia, stable mass, linear mass, and then moment of it's a little, the analogy is a little strange here, but you get regular kinetic energy and rotational kinetic energy. So let me just write this down. Rotational. And I think that's it for this. So I'm gonna stop yapping because the video is very long, and I'm gonna go to this guy. F, spring. You guys know what F is. It means force. F subscript spring is the force created by a spring. And here you have a minus sign, you have K, which is the spring constant, and you have delta X, which is the extension or the compression of a spring. That's all I'm gonna say. Let me actually just write this. Extension or compression. And then here, spring constant. And then here, force due to a spring. And there's a minus sign here because if you compress a spring this way, it's going to push back on you this way. If you pull a spring that way, it's going to pull back this way. So this little minus sign is just telling you whatever way you apply this extension, this is where the vector is on, this little extension or compression vector, whatever way you choose that to be the positive side, the spring is going to pull back the opposite way because it's like a restorative force. Don't stress about that. It doesn't really matter too much. Now we're going to move on to these two, which I'm going to put in, let's put this light blue. Check this out. We have V and we have A. These are things that you learned about over here. And you have omega and you have alpha, which are things you learned about over here. And then you have this little r. So this little r is a radius. This is all I'm going to write, and I'm going to tell you this little, I'm going to draw this little picture for you. So imagine this is r, right? And this thing is spinning around with an angular velocity or an angular acceleration. If you take a point over here, this point, as the object rotates, rolls around, let's say it's rolling around that way, clockwise, this is going to be its linear velocity at this point, and there's also going to be a linear acceleration. So this is how you can find that linear velocity at this point, at this radius, if your object is rotating with this angular velocity and or this angular acceleration. So if you have the angular acceleration, you can find this. If you have the angular velocity, you can find this. And this r, right, you can either find the linear velocity or linear acceleration, or sometimes they call it tangential because it is tangent over here to this circle. If you move into the circle, so imagine one of those like things, one of those spinning things at a playground, those like things that spin around. If you're standing on the outside, this radius is bigger, so the velocity or acceleration you feel is bigger. But if you go down towards the center and you reduce the radius, like you stand right over here, this radius has now become smaller, right? You stand right here, so your velocity and your acceleration here are going to be a bit smaller. Hopefully that makes sense. Those two equations are how you can connect linear velocity and acceleration to angular velocity and acceleration if you're given a radius. Hopefully that is okay. We're going to keep moving forward real quick. This is a very cool chapter, chapter 6. This is centripetal acceleration. This is the velo, and this is the r. We could use the same picture over here. So let's say you have like a bucket of water that's being spun around this way. Here is the r. You have the r here, you divide by it. If you have the velocity, the linear velocity at this point over here, how fast the thing is going that way, you square that number, you divide it by r, you have the centripetal acceleration. There are so many more things we could say about this equation, but right now all we have to work with, or all we should learn, is just what the units and the names of the symbols are. And this is acceleration. I'm going to guess that it has units of meters per second squared again. This is velocity. It has meters per second, and you square it, and then here you divide it by r, which has units of meters. So one of the meters on top cancels with one of the meters on bottom. This one cancels with this one over here, and the square applies to this. So you have meters per second squared, which is the same units as acceleration. So hopefully that's good. This guy, I'm going to put it just in gray because it's like a constant. I don't know. We can't really say too much about this. G, acceleration due to Earth, due to gravity. How much acceleration you feel if you just fall or if you throw an object and it's being pulled down. There's no other acceleration acting on it, like it's not in a car or anything like this. Then here we get to some stuff that I'm a little unsure about. This is the last chapter, chapter 15, I think, related to simple harmonic motion. I'm going to say just the things I know about this. So I'm going to put this all in. Actually, let's not use pink. Let's use this green over here. We'll put this all here. Sorry I didn't do any videos related to this. This here is the period, and it's in units of seconds. What does period mean? Let's say you have a grandfather clock and it's going like this, right? It's simple harmonic motion. Or you have a pendulum and it's going like this. How much time does it take to go from one side, boom, around, and then back to where it started from? Where it started from is the period of oscillation. For Earth, this is 1 year. How long does it take for Earth to go around the sun and then back? It takes exactly 1 year. If you calculate that in seconds, this is the period of oscillation to Earth. But in this case, I think this K is talking about a spring. So simple harmonic motion is seen almost everywhere in physics. If you have a spring and you pull this spring. You pull something out and the spring is both compressy and springy. The spring is going to move your object around like this, right? So your object is oscillating back and forth, kind of like a grandfather clock, kind of like the Earth moving around the sun. So it takes a specific amount of time to go to one end and then flip around and then go back to the original end. How long does that take in seconds? That is the period. You take 2 pi, which is just two numbers, no units, square root the mass of the object, and then the spring constant. This is a bit weird, but that's all I'm going to say right here. This is spring constant, and then this is mass. Let me actually check if it is the spring constant. I remember from before, spring constant has units of newtons per meter, and this is on the denominator, and here you have kilograms, and you square root this whole thing. So if I work out all these units, I should get seconds. Let's do that real quick. So I have a square root. So I'm going to use my little trick for figuring out what the recipe for 1 Newton is. 1 Newton is mass times acceleration, which is kilograms times meters per second squared. And that is being divided here by meters. This is a bit weird, but I'm going to flip this, and I will have kilograms times meters on the top divided by kilogram meters per second squared. And then here what I get is these meters cancel these meters, these kilograms cancel these kilograms, and then that second is 1 over that 1 second, so this entire thing equals seconds squared. And remember, there was a square root on all of this, so the final units for this are seconds. Amazing. So I'm kind of correct here. This has the same units as a spring constant, but like I said, you can think about period for any oscillating object. Like it could be a pendulum, it could be a spring, it could be the Earth rotating around the thing. So the K kind of changes its value a little bit. But this is mass, this has units of the spring constant. 2 pi over here has no units. That's why I left it out of my unit analysis here. And this period is the period of oscillation. How long does it take for this thing to go around? And it has units of seconds. So at least if you know this, and you see something like find blah 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 related to like a oscillating object, boom, you can put this in. And if they give you the period of oscillation and they give you the mass, find the spring constant, you can find this. I don't know, find the spring constant of Earth going around the sun. Maybe that's interesting. Who knows? Here we have the angular frequency. I think this is angular frequency. I don't know if it's exactly the same as angular velocity, but yeah, the reason I'm saying frequency is because let's look at both of these. There's 2 equations, so two different ways of calculating this, which I'm going to write over here in red. Angular frequency. This F over here is frequency, which has units of 1 over seconds, and angular frequency also has units of 1 over seconds, or radians. Like over here you can sometimes put radians or revs or degrees, right? So check this out. 2 pi is normally this thing that creates radians. So you put this in here and you get radians. So this being called angular frequency, it has this like hidden radians in here, but normally its units are something per second. When you talk about something per second, it's a frequency. How many times do you eat ice cream? 1 time per second, 20 times per second, 0.004 times per second. You use seconds, but you can convert it to days. How many times do you go to school per week? 5 times per week. Week is the time unit here. You convert that to seconds and you get a frequency. So if you have some kind of regular frequency, like how many times does the Earth go around the sun per year? It's once. So what is this angular frequency? You can multiply that by 2 pi, and then you can get that value over here. Maybe that's a bit weird. I'm kind of just speaking out my ass a little bit because like I can't really remember problems I've seen related to this, but I do remember the symbols that are here. So I think what I'm saying here is correct, but maybe I should just do a few problems to like remember what's going on, kind of refresh my mind. Anyway, that is one way of talking about this. Another way is with t, which you guys already saw over here, was the period. So if I have the period, let's say the period of the Earth going around the sun, 365 days. So if I take 2 pi divided by 365 days, but convert that days to seconds, then I have something 1 over seconds, and that is the angular frequency of the Earth. Hopefully that's okay. And these equations here, I'm going to skip through a little bit. I'm sorry about this. I'm going to just say it very quick though. X is position, V is velocity, A is acceleration as a function of time. So position as a function of time, velocity as a function of time, acceleration as a function of time, equals A, this is the amplitude cosine of omega, which is the angular frequency, times time. So angular frequency times time, these units cancel, I think, and then plus phi. This is like a starting angle. Honestly, I'm not too sure. I'm gonna have to peep some problems related to this. So this, I gotta take a look. Maybe if I find something interesting, I'll put it up here. So overall, this is the equation sheet. I also went over this very quickly. If you have any object you're interested in finding its moment of inertia, well, not any object, but any of these four objects, its moment of inertia is this. If you have an object that you don't know its moment of inertia, you could put this equation and then say, oh, based on these things, the moment of inertia combined with this, and then just kind of make some stuff up. I think you should be chilling. But this is what I would do when I start studying for this exam. So let me know if this was helpful. Let me know if you guys have any interesting questions or problems that you want me to do. In the next video, I'm going to use only my knowledge from this equation sheet, what I just spat out to you guys, and some previous experience from solving problems. I'm going to try to solve an example problem set very quickly. I'm not going to spend 3 hours on it, but I'm going to try to just go through and speak, try to give you an idea of what I think about when I'm in a final exam, and hopefully this is going to help you guys. But like I said, give me some questions in the comments, some suggestions on what you want to see. I'll try to do a video. I'm not a source of truth. I'm just trying to give you guys like some experience and some value as to like that I think is helpful. But if you guys want to see specific things, go to the book, go to your professor's notes, look at solutions of problems online. Guys, it's late. I just finished editing this whole video. Hopefully it's going to upload soon. I just want to let you guys know, please don't get mad at me if you apply these methods and you fail your exam. Like, I don't want to get in trouble for this. I'm just trying to help you guys out. For people that are like completely lost, obviously the more you study, the more you practice problems, you gotta slam problems, like do problems over and over and over. There's no way if you just study the equations like what I showed you here, you're gonna know how to do like complicated like Newton's second law problems. You guys have seen these in class maybe, or any of the equilibrium problems. Like there's some hidden things in these that you have to know about. So start off with this equation sheet. You at least know what equations are, you know what they mean, and when you read a problem, you're gonna be like, oh, I kind of know like some equation related to this. Boom, you can apply it, but practice a lot of the problems. I'd say start with the practice exam, and then like do that exam like 50 times. Practice every problem 50 times. Go to every problem from your homework. Practice every one of those problems. Review them every waking moment of free time that you have. Just keep practicing. I know you guys have multiple classes. You gotta focus and do exams on multiple classes. So focus on this. And also, little bit of like motivation. Don't worry if you fail this class. I know it's a waste of time. It's a waste of money. You feel bad because you tried. Even if you didn't try, if you fail a class, it hurts. Don't stress about this, guys. In 20 years from now, you're not gonna remember failing a class like this. Like, life is so much bigger than a grade you get on one exam in one class in 1 year of your life. Don't worry about this. Keep your spirits up. Talk to your friends and family. Physics is fun. Hopefully you guys enjoy it. Let me know if you have any questions. Stay hydrated. Very important. Eat a little bit. You know, eat some good food. Eat a fruit. Eat some oranges and bananas. Those shits get you going. And go on a walk. Like, you watch this video, go on a walk a little bit, breathe, look at a tree, and just think about this stuff. Let your brain associate it. Don't worry if you can't remember all this stuff. Like, this is crazy shit. We learned 15 This is probably like 500 pages. Maybe not 500 pages, but maybe, I don't know, 200 pages, like 15 chapters, or like, let's say 13-ish chapters of content. And like on a single one of these chapters, like Newton's laws, chapter 5, you can spend an entire lifetime on this shit and still not understand it perfectly. So don't beat yourself up. Keep your spirits high. Focus on your other classes. Speak to a friend. Call your friend up and be like, yo, what to do? You know, if you have any specific questions or anything, drop a comment. I'll answer anything you guys want. And yeah, good luck. When you sit in the exam, okay, here, exam day, let's say you wake up, Just breathe. It's okay. It's like any other day. You sit in the exam and look at the equation sheet, read through the exam, write down any first ideas that you have. I'm thinking of doing an exam video very soon, but I'll see if I have the time for this because it's quite long. Like I thought this equation sheet video was going to be 15 minutes and ended up being like an hour and a half. So in the exam, just write down as much as you can. Like do not spend too much time sitting blankly and thinking. Like think a little bit. I don't know how you guys work on final exams, but for me, I found like if I sit and think, I waste time and then I leave a bunch of shit blank and then that's where I fail. If I write something, like anything, even if it's completely wrong, if I just write something, and most of the time if I'm completely confused about something and I write down what my confusion is just in plain English, like if I don't know what's happening in the problem, I explain what I don't know is happening in the problem. These are for the long answer problems. Let's say you have 6 long answer problems. For the multiple choice, you kind of just have to guess. So go through the multiple choice really quick, try to make a guess. Keep in mind what's on the multiple choice and go back and correct it if you find some interesting new information, or sometimes your brain just like remembers some shit from deep in your mind. Go back and correct a multiple choice. But for the long answer, do not leave these blank. Write down a bunch of equations. Any equation with any symbol at all, even slightly related to your problem, write it down. Explain the equation in plain English. Write down all the units and then draw a little picture of the problem and then explain in English what you think is happening. In classical mechanics, it's easy to explain, kind of easy to explain what's happening because you can visualize it and you can say, from my experience, bop, 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 and then explain what's happening in the problem. And anytime you run into any confusion at all, no matter how simple the confusion is, it could be you forgot how to convert between units, you forgot how to do simple algebra. You can say, I forgot how to do this, I'm unsure, but I think da 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 da, and then just write some kind of guess. Or let's say you have 2 methods of solving the problem. You have one way or you have the other way. You remember one way you did it in the homework and you remember one way the teacher or the TA showed you in class and you're unsure which is the correct way. You don't want to put the wrong answer. Write down both, bro. Just be like, oh, I think this is the answer, but it could also be this. So and this is what I did. Like it feels like you might get it incorrect because you put both, and this really depends on the grader. Like if the grader really reads shit, they're going to be like, oh, this person wrote too much incorrect stuff, so I'm going to mark them wrong. But most graders, if they see something resembling the correct answer, they're going to just give you correct marks, regardless of what else is on there. So write as much as you can and explain yourself and draw pictures, write equations, draw diagrams, write in words. And that's all the advice I have to give right now. Like I said, this is a tough class. Don't beat yourself up. Keep your spirits high, bro. Yeah, that's all I gotta say. Let me know if you guys need any help with anything. Good luck. Follow all my tips. Go on a walk, talk to your family, eat a fruit, drink some water, get some rest. Listen to my videos on 2x speed while you go to sleep. This is gonna lock this in. I did this for math one time. I was doing some math and I listened to like what's his name? The organic chemistry tutor while I was falling asleep. I don't know if it helped, but I woke up and I was like, I got this, bro. And exams are fun, bro. Even if you think exams are like annoying and you're like, they never showed me this in the homework, we never spoke about this in class. That's fun. The point is to challenge you. If every exam they put shit that you know how to do, there'd be no point in doing the exam because they already know you'll be able to do it. They want to test you and challenge you. And at the end, hopefully the final grade, like the school doesn't want to fail a million students, so they're going to curve the grade up a little bit, hopefully, like I don't know. But also that reminds me why I'm filming this little final video as well. Please do not come at me angry that you failed the exam because of my advice here. All I'm trying to do is just give you as much information as possible. I'm not saying if you just memorize the equation sheet, you're going to pass with flying colors. Like basically I'm not making any claims here. I know I said in this video a lot of times, like as I was editing it, I was like, I said the word like, I promise you're gonna be good. Guys, I was just hyped, bro. I'm not promising anything, I'm sorry. Just keep that in mind. But again, let me know if you have any questions, and sorry for yapping so much. Thank you for watching. Subscribe, share this with your family and your friends, and good luck, gang. Enjoy the summertime. Look at a flower in your free time. Look at a leaf. Pick up a rock, smell it, and yeah, go say hi to friendly people in your neighborhood. Peace. Love y'all.